So just as a bit of a context, I come from the University of Manchester. I have actually 3 affiliations. One is the University of Manchester. Inside Manchester, apart from the Department of Computer Science, I'm also part of Cancer Research UK. So we do some applied research within the oncology context. I'm also part of the EDAP Research Institute in Switzerland. So all of the research having the connecting theme, explainability, and the application of specific methods in the context of cancer research in particular, but also broader themes. So a lot of the work that you're going to see today was actually done by this brilliant team of postdocs and PhD students across all these institutions, these different institutions. So in our group, we focus on 3 different perspectives of explanation. One, the more traditional explainability element, in particular how explanations interact with domain experts, in particular oncology domain experts. We also spend a significant effort trying to build explanatory models which are able to articulate natural language explanations, really centered around natural language processing. And we also have a strong emphasis on how to encode explanations which use prior background knowledge. So this would be typically in the context of cancer research, how to encode pathways within neural models, for example, so biologically informed models, and how these models affect, this type of prior knowledge affects the explainability. So today, I think in the interest of diversity, I'm going to emphasize the natural language processing side. And even if you are not within natural language processing, I think there is a common theme across this event on trying to understand how these models conceptualize, right? And natural language processing dialogues quite closely with this idea of encoding concepts and having this closer dialogue to the symbolic perspective. So just setting a bit the scene. So independent on the scientific area that you are, usually it starts the scientific workflow with some experiments and observations, right? Then one performs some analysis. But in the end, you have an end product that's a linguistic product, right? That's a statement, a conclusion that you record on a paper, right? So this is one type of artifact that you can have as an outcome of your scientific endeavor. So a statement, right? Some of your conclusions may be communicated in a table, right? Which mixture of linguistic, numerical, and some structure form, but still linguistic in nature, and depending on what you're doing, you may encode your conclusions as a set of equations, right? And what connects all of them is that all of them refer to certain sort of a linguistic structure, and they encode an abstraction of the world, right? So your conclusion is an abstraction. So what we are using as a motivation, what we have as a vision, is what if we could reason at scale over this natural language type or these linguistic types of abstraction, right? What if we could, for a new hypothesis, articulate the background evidence that's already available, right? So really this closer dialogue with background knowledge, and then build an explanation, a possible explanation, by automating this process of finding the relevant evidence and then putting together an explanation that answers to a certain hypothesis. And that's the context that I'm going to emphasize today. So how to build machines that are capable of doing that. And the way that we communicate that is as abductive natural language inference. So within the natural language community, this is how we express that. So a couple of words about abductive reasoning. Typically, abductive reasoning is a kind of poor cousin of other forms of reasoning. Inductive reasoning, deductive reasoning are more popular, referred to, right? But just to set a little bit the scene, so typically the type of reasoning that you would have in a kind of Sherlock Holmes novel would be abductive reasoning, right? So, and what is impressive about what Sherlock Holmes the character does is essentially that ability to link an observation with quite exotic background knowledge, right? So, and that's the nature of abductive reasoning. So depends a lot on background knowledge. So you have a certain hypothesis, you want to connect with the available evidence, with the available knowledge, and with the previous knowledge around that. So how can we build machines that can support this dialogue with existing facts, existing scientific facts? So to try to make it more concrete, so in natural language processing, we have the task of building machines that are able to compute a natural language entailment, a textual entailment. So given that you have a certain fact, you want, for example, to establish if this fact is true or false. It can be an entailment between, for example, two facts, a premise and a certain hypothesis. So given that you know that this is true, does the following fact in natural language is also true, right, given that fact. So, but a possible way to do that, to frame that problem is, given that you have a claim, establish if this is true or false, based on available knowledge, right? You can think about a knowledge base of facts, also in natural language, but now what is emerging as more common are, for example, tables, right? You have a mixture of tables and natural language statements in a knowledge base, and then you want to retrieve the premises which better support this statement, right? Automatically, of course, right? And then that's our notion of explanation in this context. So it's a quite different angle from explainability, but it dialogues with that notion of explainability. So how do we do that? So we have two focal points when we are building these types of models. The first one is encoding the sentence itself. So how do we encode a scientific fact, right? That can work as a premise. How do you encode the hypothesis? And of course, neural types of architectures are very prevalent in this type of text. And I'm going to communicate some of the common strategies that are used are the state of the art. So another possible focal point is to focus on the multi-hopping inference, right? The relationship between this natural language sentences, right? So how do you encode that entailment process, that relationship, which should capture the reasoning, the plausibility reasoning that we do when we look at this and then we say, okay, this is a sensible connection. There is a sensible connection between this fact. So how can we automate that? And that is a kind of entailment relation or an inferential relation. So I started with a simple example, right? So and our task collections look a lot of them like this. So simple science types of task. Right? But one of the areas that we're trying to develop is to build models which are capable of articulate expert level explanations, right? The explanations that, for example, an oncology reasoning on a clinical trial would do, that level of professional level explanation. And this is how that explanation would look like, right? So trying to articulate basic scientific facts. Some of them will have, for example, support in very basic biology, very well-known clinical facts. Others are going to be more recent types of evidence. And this is very much present in what we call experimental medicine, right? When you are, for example, some oncologists have some patients with very challenging cases. They meet in what's called a molecular tumor board, and then they need to make the assessment if there is any strategy, emerging strategy that can benefit that patient. So this is the type of reasoning that we're trying to understand, the explanations that they give to each other, and we're trying to encode the structure of these explanations as well within these models, right? So when we're talking about this, we have simpler science explanations and we have complex science explanations. And of course, the aim is that given that you have a curated set of millions of facts, which can be extracted from the literature in a quite automated way, can you build a machine that can link these facts together into an explanation? And again, it's about understanding the meaning of the sentence and connecting the sentence with a reasoning chain, right? So it's about modeling this linguistic conceptual level of reasoning. So in reality, these explanations can be even more complex, right? This is just to show you how one could make that explanation deeper, right? And they have this hierarchical nature, right? That you have a primary claim, and then you you go in this recursive nature down, and then you essentially start elaborating the other fact. So you keep asking why. So this is, I think this gives, with some concreteness, what this community is trying to achieve. So another way another type of reasoning that I'd like to do that's quite related is, in the context of clinical trials, is given that you have a certain description of a situation, a certain patient with a certain characterization, can I try to find the best clinical trial for this patient, given that I have a knowledge base of clinical trials? And these are document descriptions, and they contain certain complex concepts, right? So one of the things that's very tricky for clinical trials is that the eligibility criteria tend to be very complex. So that future, that if statement, right, that you have inside the description of a clinical trial, it's something that represents a quite convoluted type of semantic reasoning, right? And this is one of the things, practical applications that you would have for this type of inference. Okay, so starting talking about natural language, neuro-language models and methods, which are more on the neuro side of the spectrum. So when you think about the evolution, the recent evolution of natural language processing, it's very much centered around an architecture called transformers, right? That probably some of you, if not most of you, already heard. And transformers, in the end, they are language models. So they have a specific perspective on how do we understand the semantics of a sentence. And the basis of a language model, it's not necessarily neuro, right? It's trying to predict the probability of the next word, right? So what a language model is doing is trying to compute a conditional probability between the previous part of the sentence and then a certain slot that you like to fill. And of course, it doesn't need to be the last one, but you can frame this in different ways. So it uses that distributional perspective to compute probabilities, especially over large-scale corpora. So this is a cheap thing to learn because you don't need to annotate. You can just take a very large corpora and learn to compute these probabilities. And that's one reason why this is a very convenient representation. We don't need to necessarily annotate. So with this notion of probabilistic notion of a sentence, what emerged are neural network types of architectures, LSTMs, for example, that compute that probability based on that distributional pattern, right? This was a few years ago. And then an evolution of that architecture were these transformer-based architectures, which provided a quite pragmatic improvement of what these models can deliver. So essentially, transformers are encoding these probabilities as well, but they have a self-attention mechanism that allows you to represent context in a quite complex way, right? You can learn, for example, to disambiguate the meaning of words in a very expressive way. So a way to say is that they can be very expressive in the way that they are computing these probabilities. And in the end, what they are doing is they are disambiguating the semantics of these words at scale. But what is interesting about these models is that there is really no clear theoretical understanding of their behavior, right? They work for certain situations, but the guarantees of where they work, where they fail, there is not so much clarity. And what kind of world model they are generating in the end, also unclear, right? And that's a bit the tricky part of applying these models into scientific reasoning, where typically you would need to have more control. So typically one famous model that evolved in the past few years is BERT, and then what you have is a mixture of this probabilistic perspective of sentence representation and the embeddings that you have with the latent space that you just induced, right? So you can see the perspective of the semantic perspective of these models as the language model perspective or a vector representation, for example, of a sentence, right? You can project that sentence in a high dimensional space, and then you can compute similarities, and you can use the similarities and this language model probabilities to essentially solve some downstream tasks, including the one that I showed, the textual entailment, textual inference types of text, question answering. So these are all quite popular tasks. And typically you do that with a layer of fine-tuning on the top of this raw, pre-trained semantic representation. So these models, as I mentioned, they evolved, and more recently, there were some models which are really focusing on scientific inference. So there is a plethora of models that are focusing on chemical background knowledge, biomedical background knowledge, and this is one of the most recent ones. Was published in November last year, which is Galactica. Right, so this was a model that got a lot of visibility, and it's impressive what it achieves, right? So given that you have a certain prompt, right, and this is the jargon that you have, essentially that gives the context, you can do a kind of zero-shot learning, right? In some cases, you do a few-shot learning over these types of prompts that gives you a little bit of context, and then the model is able to essentially answer that question, right? And and there are demonstrations in which these models answer that quite accurately. And I think what is interesting about this model is that's mixing some modalities of data, right? It's not just natural language. It also have the chemical formulae representation and other types of abstraction, right? So such as, for example, differential equations, mathematical notations. So these models are built specialized on scientific corpora, and they have specific tokenizers that allows you to essentially organize these different modalities of linguistic knowledge, right, within the model. And they are built over quite large-scale scientific corpora, right? So these are examples of what these models can achieve, and this is really, I think, impressive. And I think the whole community was impressed how these models can do zero-shot learning, few-shot learning, and this, I think, was not anticipated and expected before, people starting doing that quite recently. However, there was a big advertisement of these models, and the achievement also is notable, right? So, but at the same time, I think 3 days later, the model was taken out because in some situations, the model was quite authoritative in stating non-factual, non-scientific facts, right? So it sounded very authoritative. It used the right scientific jargon. However, the model was failing badly in some cases, right? So it's in terms of end user, from an end user perspective, there is a gap, right, between the trustworthiness of these models, and there is still a big gap in making these models reliable, right? Still, it shows how this language model perspective can be a quite important perspective to take into account. So if we take the opposite direction, right, what would be the most controllable type of scientific inference that we could automate? We have the community of theorem proving, automated theorem proving, right? Lean is a famous and fast-evolving theorem prover. And Peter Schulze initiated, with the help of the Lean community, a program. So he's a Fields medalist, right? Trying to essentially verify one of his recent proofs, right? There is an area that he was not fully confident that he got 100% right because it's overly complex. And then the Lean community started to build a library, a very formal library, and this is not natural language processing, right? So this is people sitting, programming in this formal language, and then building a library of the dependencies which are used in this proof. So that's the opposite direction, where you have full control, and that's the value that delivers to someone like Peter Schulze. However, it's the opposite direction of what the natural language community is doing, right? So we can see language from a formal perspective as well, right? And this is something, actually computational linguistics started not with a statistical perspective, but with a formal perspective. And there are beautiful theories on how can you see, for example, language from, for example, a set theoretical perspective, right? And reasoning connects quite nicely to that perspective, right? So this would be, for example, as we are in this CLA, there was a very influential computational linguist called Richard Montague that developed the Montague semantics that essentially has the set perspective on what's happening behind, for example, the interpretation of a sentence, right? You can see, for example, the concepts that you have expressed in the sentence. If we take instability, right? When we just look at this noun phrase, increased genomic instability, you can see that it's specializing via a function application that specific set, right? So you can mathematize that notion, and in the end, when you work with language, let's say from a more abstract perspective, you see that a lot of what language is doing is putting sets on everything, right? This is defining sets of things, and then we are referring to the sets at an intentional level, right? So we have the set of instabilities, which is the most less specific one. Then we have the genomic instabilities. Then we have the increased genomic instabilities, right? And that's a perspective that's very useful if we are doing scientific reasoning, because what we are doing when we have a scientific argumentation is defining contexts in a very controlled way and referring to these contexts and to the sets of phenomena in an argumentation, right? So it's a quite complementary perspective. However, if you look at natural language processing today, I think the whole community is much more around large language models, meaning that we have representations that in some sense do not provide the same guarantees that we have under the formal perspective. And what we're going to discuss, some of the points that we're going to discuss today, is how can we harmonize, how can we integrate these two perspectives, and this is what we mean by neuro-symbolic here, right? How can we leverage the flexibility and the ability to induce semantics at scale, together with providing some controls on the top of this large-scale semantic representations. Then, let's say, to say more formally, what language models are doing a lot of the time, if we have a set of premises, this represents a set of premises, and we want to compute the entailment with a specific fact, a hypothesis, we can compute, say, this is true or false. However, typically what we would like to do is not only do that, but also deliver a proof of that, right? An explanation. And this would be our notion of explanation in the notation that you would have in the formal community, right? And this is here our notion of interpretability. And here it relates a lot to a notion of control, right? It's almost as for a scientific argumentation, for a scientific reasoning, you need to pay the price of eliciting that argument, right? Of eliciting that explanation. That's not optional. This is mandatory. Okay, so now going to the practical side, what are the strategies that we can use to essentially deliver this additional semantic control, this additional inference control? So one of the strategies that we could use is to go full formal. People did that in the past. It really doesn't work, right? If you go for a full logical representation, the logical representations tend to be very brittle, right? And what we can do is to start with lightweight semantic representation. So one thing that we have as a consequence of the evolution of statistical language models is that we have quite robust parsers, right? So essentially what we mean by a lightweight semantic representation, we can have a certain sentence, animals require food for survival, right? We can try to make it, to impose a certain structure, right? And this is a kind of semi-logical form of this that says, okay, so here I can detect that I have a verb, a predicate, right? And then I have the arguments which link to this verb, right? And this gives an initial level of structure, and at this point we can do that quite robustly, right? We essentially are not seeing that as a stream of tokens with associated probabilities between them, but we are associating a structure that puts some specific concepts in a bucket, right? And then we are telling something about the nature of this concept. So here we have, for example, an argument that talks about purpose, right? So this already tells a little bit about the structure and the semantics of that scientific statement, right? And I will use simpler statements just to make it clearer. So yes, so one way that we found quite interesting is how do we integrate this type of semantic structure, right, this more formal structure, with the flexibility that we have in language models. So how can we put that all together in a kind of truly neuro-symbolic fashion, right? So here again, we have that notion of a predicate argument, right? And one strategy that we developed is trying to use variational autoencoders and disentanglement, right, and generative models in general to induce that structure within the latent space. So we want still to have a certain latent representation, but we want to add more structure to it. So this is not too dissimilar to what people in computer vision are doing, right? Which is essentially trying to reorganize the space according to some latent factors, which are identifiable via some semantic labels, right? And then having this ability to interpolate over the specific images, right? And then then this is one of the things that we are trying to do, but now in the context of language, which has its own challenges. So one of the work that we started in this line is, can we disentangle syntactic factors, right? Can we take the syntactic structure of the sentence, which is super informative, and can we build a latent model that can learn some of the syntactic factors? So example, right? So verbs have a tense, subjects may have a certain number associated with them or gender, right? Can we identify this automatically, right? And then disentangle these factors so that we understand the structure of the sentence and we start organizing our latent space, but being more linguistically conscious, right? To abuse the term here, right? So, and then we essentially experimented with different variational autoencoder types, and then we found that yes, it's possible to start disentangling these syntactic factors, right, and encoding these syntactic factors in a more controlled way. So here, for example, you can take one statement that you have on the top, causes, and then considering that you know the latent factor that was disentangled, you can essentially change that value in terms of its temporal form, right? And then you can take the subject position and then change that with regard, for example, in this case it doesn't apply, but if it's a pronoun, to its gender, right? So, and then you can start playing with the structure, and then you are approximating the symbolic way of reasoning, which is this substitution, this ability to take one concept and then do a certain operation. Substitute this by that. Can I substitute this by that? So this points into that direction. But still, here I think it's a quite early stage because it's syntactic. So then we followed up in the direction of semantics. So, and I think this is relevant for many people in computer vision in the sense that I think there is the common goal of inducing a space that has this conceptual representation, right? And what we did here in the specific work is taking explanatory sentences, and we are focusing on corpora that we call explanation banks, right? So they are basic science facts like this. One that we are using as an example. And in the previous model, we just used as an encoder an LSTM model, right? So we're not using pre-trained models. But here we extended one architecture that's called the Optimus architecture that has an encoder model that's a BERT-based model. So it's really this large pre-trained models, and has as a decoder a GPT-2 model. And in the middle, you have a variational bottleneck that allows that continuous sentence representation with disentanglement. So on the top of this Optimus architecture, which was essentially BERT decoder with the variational bottleneck, we added a conditional autoencoder with this semantic roles, with this lightweight semantic representation. Again, semantic roles gives that structure of predicate argument structure to the fact, right? We added that as a conditional variational autoencoder. And then what we found is that you can do semantic disentanglement in this context, right? So essentially now you can do some operations over the space. So you're localizing some of the facts in the space and structuring as you would do with the faces, right? And then you localize by using this disentangled latents, right? And then you can change, say, okay, take the fact now and transform its subjects to a more abstract form, right? You can do some semantic operations, and then we are getting closer to that symbolic form, right? So what we want is essentially that concepts are localized and that we can manipulate these concepts in a more controlled way. So control here is a keyword. When we do that, we also have a better explainability on what's happening in the model. So the geometry of the space becomes that structure that you can explain better what the model is doing, right? Because if you have a very distributed model, essentially your ability to explain which latent factors are being used for a certain inference is not there. So we have control and explainability with this strategy. Right, and these are the operations that you can do. So you can do latent traversals, right? So meaning that you can take a sentence, project in the space, as you would do with the computer vision version, and then use a latent factor and change that, right? And then, so in this example here, we have the first sentence, an automobile is a kind of vehicle, and then we can do some specific traversals, for example, preserving the subject, but then changing the predicate side of it, right? Or vice versa, right? And then these are the changes that you're controlling. You're fixing something and you're changing other things. And this is due to this structure. So this is not a native property of transform-based models, but you can induce this structure using, this type of disentangling method, right? With the semantic roles associated with that. Also, you can compute some operations. So one thing that we're trying to understand is, can we have a kind of emerging type of symbolic reasoning in this type of space? So does vector arithmetic means something in this space? And it happens that, yes, we can take two sentences, for example, compute an addition, and then you would have an emergent behavior that's delivered by the vector arithmetics that you can have in this space. And you can see that there is some coherence. But this is not without noise, right? To be very clear, this is something that needs to be better controlled. So this was a first attempt of doing that. And then we started thinking, okay, how can we really add even more control on that, right? Because what you have is that not all latent factors are fully separated, right? And what we want to understand is, can we have a variational bottleneck that has a better separation and gives us this better semantic structure, this cleaner semantic structure. And what we did to achieve that is essentially to add an invertible flow-based neural network component into the autoencoder element, and then we get that better separation between the clusters. So one thing that we didn't discuss at this point is that essentially the way that the spaces are organized are by the additional structure that you impose, so this predicate argument structure, so you have the argument numbers being one of the factors, but you also have the relationship of these arguments being around a certain topic, a certain concept, right? A broader concept. And then there is a complex way to navigate on this space that you can learn as well. So you can put on the top of this, for example, a decision tree, and then you can try to learn how to navigate on this space in order to deliver the transitions between the sentences that you like, right? And this is a way that you can use to control that together with the operations such as vector arithmetic and so on, right? So this is, and then what we found is that we have better disentanglement and better separation, and then essentially our ability to interpolate, right? So we get much more cleaner facts when we take two sentences and then we try to navigate through the space and continuously deform the semantics of the sentence in a way that transforms one sentence into the other, right? So we have this smoothness, this improved smoothness in that transition. Again, there are some facts in the middle that may not be factual, right? But in this case, I think they are. But I think this delivered much cleaner types of representations. So what one can use this approach as well is to do some sort of data augmentation, right? So you can do use these spaces to take one example sentence and look into all semantically equivalent variations of that or similar to that. So this is a possibility that you can do. So because now you can control some factors and then you can vary other factors, right? So, and this is one of the strategies that we use. So we're talking about sentences that encode explanations, right? So imagine all scientific facts, basic scientific facts, more complex scientific facts. Then one part that's very important in when one is articulating a scientific argument is concepts, right? So definitions are central in any articulation of a scientific argument, right? So, and this is very much present, for example, in biology. in particular in biology, right? So if you take a sentence like this, you have a concept such as homologous recombination repair, then yeah, how do you understand this concept, right, without having control of this? So this is the other strategy that we consider quite central, and we try to apply a similar principle to what we did with the explanations with the definitions. The good thing about definitions is that they are abundant and easy to get, right? You not only find them on dictionaries, but you can clearly detect a definition, for example, in a scientific paper. So you can automatically build your definition bank, right, that captures the domain knowledge for that domain. So, and in order to impose that structure again to the definitions, we develop a typing system and then a classifier over this typing system that essentially takes parts of the definition and say, okay, this is the thing that I'm trying to define. Yeah, this is the main type of that concept, right? So this would be, yeah, the supertype of that concept, and then this specialize that supertype into something more specific, and this is a big event that we can attach to that. So it's not a very granular type of representation in order to make it feasible, right, and practical. But we found that this is a quite nice way to structure definitions and quite robust, right? So definitions tend to be quite well behaved, linguistically speaking. And then we did the same. We took the autoencoder that we mentioned before, and then we project the sentence into the space with that additional structure, and we found that we could essentially do similar operations over now that conceptual space, right? So that we are organizing that space, and again, same thing, control, ability to change the concept. So we take concept A, concept B, what's the concept that's in the middle? So you get a quasi-symbolic reasoning via this geometric navigation over that space. And again, control and explainability, better interpretability. So the way that we found that the space organized very nicely with these categories. So essentially, you are not only with the abstraction of supertype, right? It's not just taxonomic structure, but this additional specialization of the taxonomic structure over the taxonomic structure, they provide a quite nice way to control the navigation. You can say, you can go into specific types of specialization. So change this concept in direction of rephrasing that concept for a new place, right? So you can do these types of operations within the space. So on that conceptual side, right? So the way that concepts organize is clearly into a hierarchical structure. So you have very high level concepts, and then you have very granular specializations on that. So there are embedding strategies now, which are really exploring the ability to impose a geometric structure into the space so that you can reflect that ability to, in some parts of the space, concepts are too broad, so you should not have a resolution that's too high, right? In other parts of the space, you have a resolution that needs to be very granular because you are in a very specialized domain. So how can you use that ability to define a metric in this space that has essentially these properties, right? So Poincaré embeddings and hyperbolic embeddings in general are strategies that you can use for that, right? To impose that metric structure into that space. And then we did the same thing, right? We took a dictionary, a simple dictionary, but now instead of just using the autoencoder part, and not referring to any large language model, we just took that dictionary, we took that semantic row label classification, that structure, put this together into the same space using this type of hyperbolic embedding type of encoding, right? Together with that, we also used a multi-relational type of structure, meaning that a concept such as homologous recombination repair would have different relations associated with that, right? Out of the structure that we just imposed via the parser, right? And then we can essentially now recalibrate these distances via these stereotypical relationships, right? And use that to, again, structure the space, but now using a metric-like strategy. So this is an important slide. So So what we found is there are language models now that are very sophisticated, right? So T5 is one example. So, and behind T5, which is a variation of one of the language models that I just mentioned, what you have is a corpus, this what they call this colossal clean crawled corpus, which is almost 1 terabyte, right, in size, right? And on the top of that, T5 also do some training within the process. So there are some semantic tasks that T5 is using in the basic representation that the model is delivering, right? And what we did is to compare the performance of a very simple, no pre-trained model space, just simple dictionaries, right, with that additional structure and with that ability to metrify the space in that meaningful way, right? Orders of magnitude smaller, right? And what we find is that this small model beats, right, essentially T5 for most of the semantic similarity tasks that are used to evaluate this type of models, right? And this shows how unparsimonious one can be and how parsimonious one can be in terms of semantic models. So same properties, equivalent properties, and in some cases better properties with significantly smaller corpus, right? This shows that there is something off in that strategy of using large language models for everything. And that's the standard mode of reasoning today in a lot of natural language processing side, right? So this is, I think, I like this slide because it communicates, I think, quite empirically, that maybe there are alternative ways of thinking and there are more parsimonious ways that we can essentially do language-based tasks. So just to summarize that part, what we have is as a core message, right? So we developed a set of semantic and syntactic controls, right, via this very robust and simple representations, right? And we essentially have a way to harmonize them into generative model-based spaces, right? And then we can explore the structure of this space via the disentanglement operation. So this is something that you can do in natural language. This is what we did at the sentence level. So another level that we can think about is encoding the steps, right? Encoding the inference relationships. And I'm going very briefly through that, right? So what we want in the end is a model that can learn this relationship between sets of premises, a hypothesis, and then deduce, abduct over this, developing this type of reasoning. So one of the strategies that we found quite useful is that if we look at explanations, natural language explanations, they have a clear structure. So there are many categories, many relationships, and many dependencies that we can use and encode for these models to learn more efficiently how to explain. Just to give a simple example, so typically parts of the explanation is about defining things, right? So if you have a certain hypothesis, typically want to connect and unify the phenomena with a physical law, for example, an abstract fact, right? And behind the scenes, what you have is a lot of facts are trying to bridge that gap, right? So this we call grounding facts, which perform this abstraction, and this we call unification facts, right? Or more abstract facts. So just trying to detect this structure is something very informative, right? So explanations have a structure. So there is a typology that's more complex than that, but just this categorization of facts and their dependence allows us to understand better what is an explanation, right? So it has this raw structure. And you can go into a more sophisticated typology if one wants to. So what we did, and some of the tests that we work are question answering tasks, right? Given that we have, it's a kind of multiple choice question answer. And then we need to select the right answer and also deliver the explanation behind it, right? So one of the things that we did is trying to split this sets of facts into grounding and abstract facts using that categorization that I mentioned. And then trying to encode via a set of constraints the relationships that we have between these facts, right? And then having some prior knowledge that we can put in the model using this constraint. So trying to encode, okay, what is the principle behind connecting these facts, right? Because that's what we need to do. So typically we have a large set of facts, right? And then a common architecture is that we have a kind of retrieval-based model. And in this work, we did a very simple BM25 type of retrieval. So we retrieve a set of relevant facts using a relevance function, right? And then after that, over that subset, now we need to connect the dependencies between the facts, knowing that we have a certain hypothesis, right? That drives that explanation, right? So one of the things that I think it's also an important message is that we can integrate some prior knowledge on how do we connect this fact. So one of the things that we did is a notion of saturation. So we need to try to, if we have a statement like this, we need to connect parts, right, or subjects, arguments in one fact to arguments in that fact, and we need to maximize what we call the saturation, right? We cannot leave arguments which are unmatched. So we can try to maximize that. And then we can encode that with a score, right? And this is quite relevant prior knowledge, right? That's an example of saturation. We have other types of scores that we use, but I'm not going through them in detail. And then we can try to learn via, for example, a kind of IOP-based optimization. We can try to learn over these constraints that we just defined, right? So, and this is what we found is that this also delivers a quite parsimonious model on how to connect these facts in comparison to trying to do that via a large-scale language model, right? So a little semantics really goes a long way in this case. So then the next step, what we did was, okay, in this case, we are not really using large language models as an input, right? Because there are some complexities on doing that. So we developed a model that aimed to essentially use a relevance function that has a sentence representation using a transformer, right? So, and this is that part here. So we have our knowledge base now encoded as SBERT-based representations, really these full embeddings, complex embeddings types of representations, right? Then we retrieve that using that latent based representation. And then we have an end-to-end model that can train over that representation within a neural network, right? So, and then we are using essentially differentiable convex optimization layers to impose the constraints that we just spoke before, that prior knowledge. So similar to what we did, the notion of saturation, for example, right? And then we can learn the weights on how this connect in an end-to-end fashion within a neural network. So it's a way to integrate the representation that we have, the BERT-based representations that we have, which are quite flexible and expressive, right? But to impose the constraints on the inference that we know, right? That we can leverage, right? And then that architecture that we call the diff explainer is that end-to-end way of training it, right? And there were some tricks that need to be performed in order to do that. So to summarize that multi-hop element, so I think the core message is that there is a lot of prior knowledge in the structure on how inferences are working that we can develop and that we can integrate within the architecture of the models, right? And that ability to match, to have a kind of neural solver where you integrate that sentence representation, which is typically transform-based, with the constraints that you have on how to connect the sentences with that control is something that's we consider quite a quite efficient way of doing that. So just to wrap up, I'm going to just mention some of the works that we are doing that we consider quite exciting areas of working. So far we are talking about encoding natural language statements, but there is a quite significant community growing on mathematical language processing. So, and this is essentially trying to do similar operations over textual mathematics, right? Not really formal mathematics. So have a knowledge base of premises extracted from papers, from textbooks, and then you try to prove or at least find the relevant premises which support that conjecture. And of course, you need to have the ability to interpret equational reasoning and to deliver equational reasoning to do that. So there is a nice community, and we have some work on this area as well. So still quite related for scientific inference. Another area that we consider quite strategic if you're dealing with reasoning is really on the evaluation of if these models are really doing reasoning or they are using artifacts, which is not the standard practice in NLP, right? And there are some quite solid methodologies emerging on how to do that, right? Interventional studies where you try to look into some specific phenomena within the model, semantic phenomena, and then you try to have a causal intervention within that phenomenon. So quite interesting area as well. And I think it's very much connected. A lot of these models get the answer right for the wrong reasons, right? And at least in NLP, it's not common practice that you essentially do this type of, let's say, better designed semantic studies. But I think the community is catching up. Final point that I consider quite strategic as well, in natural language processing, there is a community that is working on table to text entailment. So given that you have a knowledge base of tables, determine if this fact is true or false based on the information that's on the table. This mix numerical reasoning with linguistic reasoning. Quite exciting area as well. So just to wrap up, so I hope that I could communicate some emerging strategies that I think are very promising in order to marry the flexibility of the neural language models with the control that's required, that you get from the formal perspective of language, right? And the idea is essentially that you can control some of the properties which at the moment are not controllable in large language models. So sentence level encoding strategies, disentanglement can be a very promising approach depending on what you're trying to do. Robust, lightweight semantic representations. This allows you to organize, to impose a structure into your semantic space. And then there are specific methods that you can use to represent concepts, complex conceptualizations, and abstract statements. On the inference side, you can exploit the structure of the reasoning that you can already integrate as prior knowledge. And there are architectures that allows you to integrate that essentially with transformer-based representations, right? And differentiable convex layers are a mechanism to do that. And then to evaluate using the true inference properties and always aim for that, because the presence of artifacts in most of these evaluations are quite significant. So thank you for your attention. If you have any questions, be glad to share.